Let's start off with the very first question of this paper. This question tells us to find the values of k for which, for all real numbers x, the expression given is positive. We are given a number of ranges here, but how exactly do we approach this problem? As you can see over here, we have a quadratic equation, and therefore, let me introduce you to quite a useful approach. It's called completing the square. So, what exactly is completing the square? Completing the square is a method where a quadratic equation is expressed in terms of a square which depends on x plus a constant independent of x. So, how do we express this quadratic in the form, assuming that a is a positive real number? Firstly, we factorize a out from the expression, and then we do some algebraic manipulation, which leaves us with this form. This method is useful as we now know that all these quadratics in this form where the small letter a is a positive real number must be greater than or equal to a certain value, since the left hand side of the bottommost equation is always a positive number. Now let us use the method that we just learned. We first complete the square in the expression given, and after doing some algebraic manipulation, we end up with this. This is the equation given to us in the question, expressed in the completed square form. This equation shown here is the equation given in the question but expressed in a completed square form. We know that the expression is positive for all real numbers x if the right hand side of the above equation is more than or equal to 0. This inequality is equivalent to this another inequality over here, and we can use the complete the square method again to yield 3 times the square of half of k plus 1 is greater than 3, or half of k plus 1 squared is greater than 1. This implies that the term in the square brackets must either be greater than 1 or less than negative 1, which implies that this is the range of k, and the answer is therefore option D. This question gives us a series of log arithmetic terms and tells us to simplify it. But how do we handle log arithmetic terms? Let's see. Let us recap the rules of logarithms which will be useful when solving Math Olympiad problems. The definition of a logarithm is that if x raised to the power of n equals a, then log base x of a is equal to n. So by definition, log base x of x to the power of n equals n. Firstly, we have the product rule, which states that log base x of a plus that of b is equal to log base x of the product of a and b. The quotient rule says something similar. Then we have the power rule, which states that log base x of any real number a raised to a certain exponent is equal to that exponent multiplied by log base x of a itself. And lastly, this is the change of base rule, which will be useful when we need to change the base of the logarithm. Now let's go on to apply these rules to the problem itself. Notice the equation given to us in the question that we are supposed to simplify. Notice that there's a lot of addition and subtraction of logarithms, and therefore we can use like the product rule and the quotient rule as seen below, where we deal with addition and subtraction of logarithms, but notice that they deal with logarithms of the same base. So how do we convert these logarithms to the same base? Well, we use the change of base rule to convert all of them into log evident base trees. And by the power rule, log base 3 of 9 equals 2, since 9 equals 3 squared, and the same thing goes for log base 3 of 27 equals to 3. Therefore, you get this equation here. But now we want to get rid of these fractions. We can use the power rule again on 16 and 8. And we converted to this form, and notice that the indices above the 4 and the 2, they cancel out the fractions. And then we finally use the product rule and the quotient rule to get the following log base 3 of 24, giving the answer D. Now we have a problem telling us to solve for x in an equation with powers of 7. But how do we solve this equation? Let's see. This here is the equation where we're supposed to solve for x. Notice that we have a 7 raised to the power of x minus 1 and 7 raised to the power of x. Why not we make it the same? Why not we change this 7 to the power of x minus 1 to a 7 to the power of x? We can do this by multiplying both sides by 7, which gives us this equation here. And since we have two 7 raised to the x power terms, we can use the substitution to substitute u equals 7x. Notice that here we have a u term and a reciprocal of u term, which we want to solve for u. But how do we solve for u? We turn this equation here into a quadratic equation by multiplying both sides by u, and after factorizing, we get u plus 7 times u minus x equals 0, and the roots of this equation are therefore u equals negative 7 or u equals 6. However, u equals 7 raised to the power of a real number x. Therefore, the number u must be strictly positive, and therefore u is equal to 6. And since 7 raised to the power of x equals 6, x is log evident base 7 of 6, and the answer is therefore option C. In this question, there is a polynomial that is unknown to us, but it is known that when they are divided by two different divisors, they yield two different remainders which are made known to us. We are told to find the remainder when it is divided by another divisor, which is x minus 1. As I said earlier, when we encounter a quadratic, in this case a quadratic divisor, we can try to factorize it. Notice that the right hand side factor is one of the divisors provided in the question just now. Notice that we can rewrite this polynomial in this form, since we know the remainder when divided by x minus 1 times x minus 2, as well as the remainder when divided by x minus 2. Now let me introduce you to this theorem called the remainder theorem. When you divide a polynomial p of x by the term x minus a, the remainder is p of a, which is obtained when a is substituted for x in the original polynomial equation. Therefore, p of 2 equals to 11, as the term containing x minus 1, x minus 2, qx is equal to 0. Therefore, ax plus 5 is 11, and substituting x equals 2, and then solving for a, we get a equals 3. And so the remainder, when p of x is divided by x equals 1, is given by p of 1 by the remainder theorem again, which is equal to 8, which gives the answer B. This question deals with lots of surds, which are like square roots and cube roots. But how do we simplify it when the denominators are not the same? Let's find out. When encountering questions with certs, these two properties might be useful. As you can see here, we can factorize a cube plus b cube or a cube minus b cube into different factors. And when we encounter questions with certs, we sometimes can substitute a cube or b cube for a square root or cube root. And therefore, in the original equation, which is this, we can factorize out the cube of square root 5 and the minus the cube of square root 2, as well as the sum of the cube of square root 5 and the cube of square root 2, which gives us this. Notice that the numerator and the denominator of the left-hand fraction both have root 5 minus root 2, and something similar for the fraction on the right, and therefore we can simplify it to this, and after simplifying we get 2 root 10, giving the answer B. In this question, we are given an angle A and a range that angle A can be in, and we are given 5 expressions which we are told to find one of them that equates with the given expression in the question statement. How do we encounter this problem? Let's see. In the question, we were told that angle A is between 270 degrees and 360 degrees. You also need to know the trigonometric functions in the equation. Like in the equation, there was sine of A and cosine of A. And when we want to find out whether they are positive or negative, we can use something useful called the 4 quadrants. But what are the 4 quadrants? All angles will fall in one of these 4 quadrants as seen in the first picture. If your angle is between 0 degrees 90 degrees, it falls in the first quadrant, and then if it is between 90 and 180, it falls in the second quadrant, and so on. In this case, our angle is in the fourth quadrant, as it is between 270 and 360 degrees. From the pictures in the previous slide, we know that since angle A is in the fourth quadrant, sine of A is negative and cosine of A is positive. This is the equation given to us, and therefore we factor out cosine A from the equation, and now we get this over here. This means the absolute value of cosine A and the absolute value of sine A. But since cosine A is positive, the absolute value of cosine A is equal to cosine A itself. But sine of A is negative, which means that the absolute value of sine A is equal to negative sine A, and therefore the minus signs cancel out to give this expression here, which is equivalent to option A. Over here, we are tasked to find the range of values of x which satisfy two different inequalities, but how do we deal with range of values of x? Let's find out. The first solution which will be presented here involves completing the square. Firstly, we expand the first inequality and simplify it, and then after that we complete the square on the equation, and then we find the range of values that satisfy this inequality. We do the same thing for the second inequality, and so now for both inequalities we know the range of x that satisfies the inequality. We can also do this with an alternate method which involves factorization. It will be presented on the next slide. This alternate solution involves factorization instead of completing the square. We do the same first step where we expand the first inequality, and simplify it. But after that, instead of completing the square, we factorize it to get this equation here. In order for the left hand side to be greater than or equal to 0, both of them must be either positive or either negative, and therefore we can find the range of values satisfying the inequality. We can also do the same thing for the second inequality. Now, for both inequalities, we know the range of values of x satisfying it. The red line represents the range of values of x that satisfy the first inequality, while the blue line represents that of the second inequality. But in order for a value x to satisfy both inequalities, it must be an overlap of the red line and the blue line. As seen in the number line below, the only values of x that lie on the overlap between the red line and the blue line are 2 less than or equal to x less than or equal to 3, therefore giving us our answer option C. This question gives us a domain of x and tells us to find the range of f of x where f is a function. But how do we solve this problem? Let's find out. As I mentioned earlier, when dealing with ranges of inequalities, we can try like two methods like factorizing or completing the square, but we can do neither of this when there's a square root term inside the equation. How do we get rid of the square root term? It's simple, we just substitute the square root term for another variable u, and so after that we find x in terms of u, and the range of u is also given 0 less than or equal to u less than or equal to 4, since the equation stated that that x is between -4 and 0 inclusive. And so therefore f of x is given below in terms of u, which we simplify by completing the square over here. And given the range of u, we know that u minus 3 squared has a minimal possible value of 0, which happens when u is equal to 3, and therefore the maximum possible value of f of x is 20. But what is the maximum possible value of u minus 3 squared that satisfies the range of u? It is simply when u is as far away from 3 as possible, and therefore the maximum value is 9 when u equals 0, yielding the minimum possible f of x of 11, and therefore the range of possible values of f of x is therefore option E. This question is a coordinate geometry problem wherein we are given the equation of a circle and are told to find the equation of the tangent line to the circle of it. So let's find out how we can solve equations which handle coordinate geometry. When we are given the equation of a circle, we first want to find out its center and its radius. But how do we do it? This is a standard equation of a circle, and when a circle is expressed as such, we can find out from the equation that the circle is centered at the point hk in the xy plane and has a radius of length r. But we were given a circle in a general equation. How do we convert it to a standard equation? This is the general equation of a circle. We first complete the square on all this, and then after that we simplify it to get this. And so, applying this method on the equation of the circle in the question, the standard equation of the circle is given as such, and therefore this circle with side length of 5 units is centered at a point x equals 2, y equals -4. Now we want to find out the equation of the line tangent to a certain point on the circle. Recall that the equation of a line is given by y is equal to mx plus c, whereby m is the gradient of the line and c is the y-intercept. But we don't know the gradient of the line, neither do we know the y-intercept. So what do we do about this? Well, we can find out the equation of the radius of the circle which touches that point. The gradient of the radius is given as such, and we substituting the xy as the center of the circle as well as the point that we are supposed to find the tangent line of, and therefore you can obtain the gradient of the radius from the center of the circle to that point on the line. Since the tangent is perpendicular to the radius, the gradient of the tangent is given by -1 divided by the gradient of the radius, which equals to 4 divided by 3. Therefore, we can substitute in m equals 4 over 3 into the equation of the tangent, and therefore it is equal to y equals 4/3 x plus c. But how do we find c? We know that a point -2 and -1 lies on the tangent line, and therefore we substitute xy equals -2, -1, and we therefore can find the value of c from here. We put the value of c back into the equation and move the numbers around, getting 3y minus 4x minus 5 equals to 0, giving our answer option A.